Okay, thank you. The motivating question for our work is just, out of curiosity, what can we say about the quantum query complexity of regular languages? Quantum query complexity is some measure of how difficult it is to compute a function with a quantum device, and the regular languages are a nice, simple set of problems to test this on. And so what we found was sort of surprising. This measure of complexity divides the regular languages into three classes, sort of easy, medium, and hard, in a very discrete way that we don't expect from query complexity. And so we dug into this a little more, characterized these three classes, and proved a theorem, and along the way we found some interesting applications as well. So I'd like to tell you about as much of that as I can. Of course, I have to start by introducing the query complexity and quantum query complexity, and also the regular languages. Then I can state the main result and maybe a tiny bit of the proof, give you some intuition for how we get these algorithms, and then applications and open problems with whatever time I have left. Okay, so query complexity. So the setting for query complexity is you have a language and you want to know how hard it is to decide membership. And we're all familiar with like time complexity or space complexity, where you're measuring how much of some resource you need to compute the function. And this is as a function of the input length for the best algorithm in the worst case. This is all familiar stuff. And query complexity is the same thing, but with input queries, right? It's a sort of an unusual resource. You don't even usually think about how much it costs to query the input, but that's what we're looking at. So we're going to make it explicit. The input is entirely hidden, except for the length, and you have to pay to reveal input symbols. Okay, that's what costs you. And you can do this anywhere in the string, adaptively. All other computation is free. All right, so at the end of the day, all we care about is what's the minimum number of queries to decide if you're in this language. So here's a quick example. The AND language is the set of all bit strings where every single bit is 1. The AND of the bits is 1. And if you were given a string of length 4, say, at the beginning, you don't know what any of the bits are, so you can't decide if you're in the language. You have to reveal one of them. If you're lucky enough to reveal a 0, then you're done. There's no string of the form, say, blank 0, blank, blank. But if you reveal a 1, you have to keep querying, okay, all the way down the tree in this case. So for this example, the query complexity is 4. And in general, on inputs of length n for this language, it'll be n. But this is deterministic query complexity. We care about quantum query complexity, right? And so that's just exactly the same thing, except the queries are now quantum, right? So the key is that we're able to query in superposition. And so formally, we set this up with a quantum oracle that's doing the indexing in some reversible, quantum-friendly way. And then we just count how many of these we need in a quantum circuit to solve our problem. All right, so let's do an example. What's the query complexity of the AND language for quantum? Well, you're probably familiar with Grover search if you're in this session. So there's an algorithm that searches a list of n items for a marked 1 in square root of n queries. And in particular, this applies to AND because we can search for a 0, right? If we find a 0, we know the string is not in the language. If we don't find a 0, we assume it's all 1s, and therefore it's in the AND language. So we get this square root of n query algorithm. And it turns out there's a matching square root of n lower bound for the same language. All right, while I'm here talking about Grover search, I want to introduce sort of a fancier version of Grover search that I'll need later. I called it fancy Grover search. And it says that if many of the items are marked, say at least t of them, then you get a speed up. The algorithm runs even faster. Specifically, you only need square root of n over t queries to find a marked item instead of square root n. So in the extreme case where t is n and all of the items are marked, you can find one in constantly many queries. Not really surprising, but we'll need this later. All right, so that covers query complexity. Now I want to introduce the regular languages. So this is a very old family of languages. Predates Fox, I'm sure. And it's usually defined as a sort of handful of basic regular languages closed under 3 operations. So the basic languages are the empty language, the language containing just the empty string, and for each symbol in your alphabet, the language containing the string of length 1 that is just that alphabet symbol. Okay, very simple building blocks. And then you close them under union, concatenation, and cleany star. And so union is self-explanatory. Concatenation is you're taking a string from one language and a string from the other and concatenating them. And cleany star, you're just concatenating some number of words from a single language, really. Any number. And okay, so simple examples. You can take a bunch of these single letter languages and get a word. You can take a bunch of words and union them together to get any finite language you like. But of course, the point is you also get infinite languages, like the set of all strings, or the AND language that I showed you earlier, or a related OR language, the set of all strings containing a 1, or even parity, so the set of strings containing an even number of 1s. All of these are regular languages, and some of them are familiar in query complexity already. The expressions I've given here describe how to sort of build up each of these languages from the component parts, but there are other definitions of the regular languages you might be more familiar with. In particular, you might have seen finite automata. So, right, deterministic or non-deterministic finite automata recognize the regular languages, and there's a whole bunch of other definitions based on grammars and logic and algebra. We're going to skip all of these for most of this talk. But that's the regular languages. So now I can sort of start to present the main result. And I want to do this by just looking at some examples. What are query complexities of some sample regular languages? So the empty language, what's the query complexity of this? Well, 0. You don't have to look at anything to know that you're not in the empty language. Then we have, say, the set of all strings starting or ending with 0. Well, there's an obvious algorithm. You look at the first bit, you look at the last bit, and so the query complexity is at most 2. Then we have the OR and AND languages. We've seen AND before, right? We can Grover search for 0 to prove that the string is not in the language, or in the case of OR, we Grover search for 1 to prove the string is in the language, but in either case, we get a square root n query algorithm, and there's a matching lower bound. And then parity. So parity, it's easy to see deterministically that you need to look at every single bit. And quantumly, it turns out you get a factor of 2 improvement over this. There's a trick that lets you query or compute the parity of 2 bits with 1 query. But that's all. So it's linear complexity. And similarly, if you look at computing the Hamming weight mod k, you need linearly many queries. Okay, so if we look back over these examples, we had 2 that were constant query complexity, 2 that were square root n, and 2 that were linear. And if you keep doing examples, you'll keep seeing these 3 cases. Okay, I don't have time for any more examples, but that's what you get. And so our theorem is that every regular language has quantum query complexity constant, square root n, possibly with log factors. We haven't been able to remove that, or linear. Okay, and we also characterize the 3 different classes. So the easy ones, the ones that require only constantly many, you can decide by just looking at constantly many symbols on either end. So like the language that was strings that begin or end with 0 is a good example. The easy and medium languages together define or comprise something called the star-free languages. I'm going to get to those in a second. They're another old family of regular languages. And so the medium ones are the star-free languages that are not already easy. And then by process of elimination, anything that's not star-free has to be hard. Okay? So that's the classification. As I said, understanding the star-free languages is essential to understanding what's going on here. I just want to deal with sort of a technical issue first, which is that it's possible to define languages where the query complexity isn't technically one of these things. It sort of oscillates between, say, 0 and linear, right? On even length strings, it's linear. On odd length strings, it's 0. And this technically breaks our theorem, right? It's a combination of two of these classes, but technically it's none of them. And so the way we're going to deal with this, at least for this talk, is to just redefine query complexity. We're going to say it's not the worst case over strings of length exactly n, it's the worst case over strings of length at most n. And this sort of makes things monotonic and fixes our problems. This example will be linear, and this part of the theorem is true now. So right, back to the star-free languages, because they're the key part of this. So the star-free languages are defined the same as the regular languages, except you're closing under 3 slightly different operations. So you still have union and concatenation, but you drop cleany star and pick up complement instead. Okay, hence the name star-free, because you've dropped the star operation and replaced it with something else. And so you get most of the same languages you saw before. The empty language, the set of all strings. Now it's the complement of the empty language rather than sigma star, but it's still the set of all strings. You can get or and it's a little bit more cumbersome, but you can express them in terms of these operations. But it turns out you can't express parity in here. So it is a proper subclass of the regular languages. All right, so that covers the theorem. You sort of understand the result now. And what I want to do from this point is look at a sort of complicated star-free language and show how we get a fast quantum algorithm for it, because this is sort of an instructive core piece of the proof. Right, the languages we've seen so far are both fairly easy. Or and are both solved by a single Grover search. That's not interesting. Let's look at something that is. And so the sort of challenge language we'll define, I'll call and or. Okay, so this is a language over a hash symbol, 0 and 1, and the rule is there needs to be a 1 between every pair of hash symbols. Okay, another way to look at it is the hash symbols divide the string into a bunch of blocks, and you want each of those blocks, each bit string, to match the or language. Okay, so it's sort of an and, all the blocks have to satisfy the or language, and thus and or. Again, and or is a language that, or a function that's familiar to query complexity theorists. Anyway, it's regular, but we really need to show that it's star-free. And indeed, there is a star-free expression. I'll leave it as an exercise to check that this is correct. And so if our theorem says that this should have a fast square root of n algorithm, what is it? Let's figure that out. So what we're going to do, our strategy is to prove that the string is not in the language. We're going to search for a block where there's not a 1 in between, where it's of the form hash 0 star hash. Okay, so how do we do this? Well, we have to Grover, otherwise we're going to be too slow. So we're just going to Grover search for some position contained in this substring. Those will be our marked positions, positions in this string. And testing whether you're within the string is not trivial, so we need to write a subroutine to test whether the item is marked, right? And the way we do this is we start at the position I and scan outwards to a non-zero in either direction, right? If both of these non-zeros were hash symbols, then we'd be done. We'd have a block and our index should be marked. If one of them is a 1, then clearly the block containing I also contains a 1, and so it should be unmarked. All right? So this works. The unfortunate part is the complexity. So Grover search runs square root of n steps, and we run this subroutine each time, and in the worst case, it could scan the entire string. It could take linear time every single iteration. And so we need to do something about that. So attempt 2, let's use more Grover search to fix this. And so what we'll do is instead of scanning linearly, we'll do an exponential search outwards to find where the zeros stop. Okay, we'll look 1 step, then 2, then 4, then 8, until we see a non-zero, and then sort of binary search into where they stop. And the reason we can do this is we can search large sections of the string with Grover search, right? It only takes square root of n time rather than linear. So it is an improvement over just a straight scan. Right, here's an example. We search 1, then 2, then 4, then 8, except we find a non-zero, so we binary search in between. We're still doing the same thing before, locating the nearest non-zero on either side. We're just doing it with a sort of fancier search algorithm. Okay, so this improves on what we had before. It's dominated by the cost of the longest Grover search that we do. And if the run of zeros that we're looking at is length L, then that'll be square root L. But since we have no bound on L, it could be square root n, and so our whole algorithm together will be linear. All right, so attempt 3. This will be the one, right? So imagine that we knew there was a block of length exactly L. Could we make this faster? Well, yes. The marked item subroutine could stop early. It only needs to search about distance L in either direction, and then it can give up. And also the outer search runs faster. Turns out there are a lot of marked items, right? If the string, this block, is length L, then every position within it counts as a marked item. And I said that when you have many marked items, the search is faster. So you get this square root of n over L iterations. And now there's some hope, right? If we set up our algorithm to stop after that many steps on the outer search and the appropriate number of steps on the inner search, then those square root L factors will cancel out, and we'll get a square root n time algorithm. So the only problem with all of this is that we don't know what L is. We don't even know that such a block exists. But we can use a sort of an old algorithmic technique of just guessing L, right? We try L equals 1, L equals 2, 4, and just double in an exponential series. At some point, we'll be within a constant factor of the correct L, if one exists, and then we'll succeed. Otherwise, we'll scan the whole thing, and we can stop then. And so we're running this whole procedure log n many times, so we pick up this log factor. We don't know how to remove that or whether it's possible, but right, so that's the algorithm. So why is this important in the more general result? Well, what we just solved is sort of an infix search. We solved the problem of does there exist a substring belonging to some particular language? And what we show in the paper is that we can decompose a star-free language as sort of a Boolean combination of infix searches and also suffix searches and prefix searches of simpler languages. And then we have this sort of recursive many levels of Grover procedure. Okay, so in the last minute or so, I wanted to talk a little bit about applications of this. So one neat thing that got at least one of my co-authors involved is there's this connection between star-free languages and first-order logic. And so, for example, OR is, does there exist a position in the string that is 1? And are all the positions in the string 1? And so on for and OR. And if you think of Grover search as solving one of these, it solves the cases where there's one quantifier. But languages with arbitrarily many quantifiers are still star-free. And so our algorithm applies and sort of generalizes Grover search. Let's see, you can also look for paths in grids. We can't do the general case, but if your grid is very narrow, right, one of the dimensions is constant size and the other is very long, then you can cast the problem as a star-free language and you get a square root of n query algorithm. And then suppose you want to just check if two integers sum to a third. Again, you can cast it as a star-free language problem, and so this can be solved in square root of n queries. All right, I guess one last thing before I give up. There's an alternate characterization of the three languages we talked about in terms of more familiar circuit classes. So you can look at the easy ones as NC0 intersect the regular languages, and the medium ones are sort of AC0 things intersect the regular languages, and so forth. But if you were hoping that maybe all AC0 languages have square root of n query complexity, I'm afraid you're out of luck. There's a result that surjectivity requires nearly linear complexity. So thanks. That's all I have. We looked at context-free languages. I have a slide on that somewhere. So the sort of natural thing to look at after regular languages are the context-free ones, and we show that actually for every computable C, you can get a query complexity of like n to the C, at least within this interval 0.5 to 1. We don't know what the actual story is, but you see it is much more continuous than these three discrete things.